We'd like today to be joined by Ryan Roussel, who's joining us today from the SLAC National Accelerator Laboratory at Stanford. And he's going to be talking about Xopt and Badger, an ecosystem for advanced particle accelerator control and optimization. So if you're ready, Ryan, feel free to get started.
Yeah, thanks for the introduction, and good afternoon to all of you. Although, of course, it's still early morning for me here in the United States, but it's good to be with you all. So yeah, today I'll be talking about advanced particle accelerator control and optimization using machine learning. So let's just get started. So particle accelerators are some of the largest, most complicated devices we've produced as a species. Some of the examples that we have of these massive facilities include the accelerator that we have here at SLAC, as well as the accelerator complex at Fermilab, and for example, the Large Hadron Collider in the EU. And so when we talk about using these facilities for scientific research, we need to consider that this complexity requires a massive team of human operators and specialized physicists in order to get these machines up and running and to maintain their performance over time such that they can be used for experimental science. So for example, we have this accelerator facility at SLAC, which is called the Linear Coherent Light Source, or LCLS. Essentially, what we do at this facility is we take electrons and accelerate them and compress them such that we are able to get them to a very high energy, GeV scale, and then send them through what's known as undulators, which wiggle the electrons back and forth, and they produce light. And that light is used for ultra-fast imaging at the attosecond scale, probing material science and chemical reactions, so on and so forth. However, to get this nearly 1 kilometer long machine up and running, we have to spend a significant amount of time configuring and tuning the accelerator for all of its different use cases. So to give you an example, the approximate annual budget of LCLS facility is about 145 million US dollars. And essentially, this equates to about 30K or $30,000 per experiment hour to run. And we spend about 400 hours of the overall operating machine time over the year in hand tuning the accelerator. This is adjusting accelerator parameters such that we transport the beam through the accelerator, and the beam quality is maintained throughout in order to deliver photons to our users. And so essentially what this equates to is on the order of $12 million of lost science that we could be using for experimental purposes. And so the goal, similarly, we also in physics have a substantial, we do beam dynamic simulations and physics simulations of the physical processes that happen inside of our accelerators for electron beam transport and generation. And all of these simulations are fairly computationally intensive. And so they use potentially tens to hundreds of node hours on high performance computing clusters, such as Perlmutter at NERSC. And we would like to reduce the computational expense of running these simulations when we're performing optimization. And so there are just some examples of this here, start to end simulations of the accelerator facility that I was just talking about, something called laser wake field acceleration, and then also beam generation from hybrid gas solid materials. And so when we talk about doing optimization and control, essentially there's been there's a breadth of development in terms of creating different types of optimization algorithms. Some of them are conventional, so things like Nelder-Mead simplex, or use other types of heuristics, such as genetic algorithms. or so-called evolutionary algorithms. And then some of these are also machine learning based. So for example, a very popular one in the accelerator physics field is Bayesian optimization. And so connecting these algorithms to the optimization problem that you're trying to solve is a challenging case because each different optimization algorithm has its own interface. Each problem has its own interface. And so connecting these two together is a barrier towards doing frequent optimization and leveraging all the advances that we've made in machine learning-based optimization algorithms. And so the goal of the Xopt ecosystem and the Xopt package is to specify a framework that easily connects generic optimization algorithms to generic optimization problems. And so this framework is independent of the problem type. So if we have either a simulation or experiment, we can use the same algorithm on both. And it's also independent for via optimization algorithms, so you can switch out algorithms very easily. And one of the most important things is that to get non-experts in the optimization field to use these algorithms, we need to make them as easy as possible to use. And so we want to create a overall ecosystem that allows user or non-experts to use the code, but is extendable for experts to solve really challenging problems. And so this is what the Xopt system Xopt ecosystem looks like. It contains two main packages, Xopt and Badger. And so essentially what happens is that Xopt is the core optimization framework that specifies a framework for communicating between algorithms and arbitrary optimization problems. And then depending on the use case, Xopt can be used via a variety of ways. So for example, in high performance computing clusters, you can specify Xopt runs using a basic YAML text file. For research and development, you can use Xopt via a Python interface. And then once you have done some kind of R&D and you want to transition this to regular operations for non-experts, this is when you go to start using the Badger GUI, which is essentially just a graphical user interface that goes on top of Xopt that communicates with accelerator control systems or arbitrary scientific control systems and provides a visual for non-experts to use without having to do any coding. And so essentially what this talk will cover is we'll go over the Xopt framework itself and talk about a number of different case examples of what it's capable of in terms of the research and development that we've been doing into this package over the past couple of years. And then I'll also give a quick overview of the Badger interface and show how it's being used at accelerator facilities across the world. So to start out with, we can talk about the very basics in terms of the Xopt structure. So Xopt contains 4 major classes. The first class that I'll talk about is VOX, which is variables, objectives, constraints, and depending on your reading of the S is statics. Essentially what this does is it defines the problem space. So it defines what things we're looking to tune or optimize, or sorry, what parameters we're able to adjust. And then the objectives are, of course, what we're looking to, for example, maximize or minimize. And then we can specify observable-based constraints. So things like making sure that the beam is not destroying any of our experimental equipment. This VOX is then put inside of what's known as a generator. And this generator is the implementation of our optimization algorithm. And so the generator generates sample points that are then passed to the evaluator, which is essentially the logic of our problem definition itself. The evaluator evaluates the objective function and then is able to return those values back to the generator in order to generate the next point. And this control flow happens inside of an orchestration object, which is the main Xopt object. And for ease of use, we have an xopt.step method, which essentially does a single optimization loop where a generator will generate a point that's evaluated by the evaluator, and the evaluator returns the information from the evaluation. And so this is a very basic sequential example. More complicated orchestration is possible via the Xopt asynchronous package, and this allows asynchronous generation of points and evaluation of points. So one of the key aspects of making this process extensible to almost arbitrary problems is by specifying a very simple interface that we require in order to communicate with our optimization problem. And so essentially users of Xopt define a basic Python function that the only rules is that it takes in a dictionary and returns a Python dictionary. And these dictionary inputs and outputs have to correspond to the labels of your variables and objectives in the next slide that I'll talk about in the next slide. And so essentially by specifying this very simple interface, we're able to connect Xopt to a wide variety of problems, essentially because Python wrappers around control systems or simulations are so ubiquitous. So essentially, as long as we can write this basic Python script, we can optimize it inside of the context of Xopt. And then the important thing here is that the inputs and outputs of that dictionary have keys that correspond to the naming convention of our variables, objectives, and constraints. So this is a very basic example here where we're trying to minimize a function f subject to a constraint g over the variables x1 and x2. And essentially, we encode that information into our Vox object. And then inside of our example evaluator function, we just create an evaluate function that computes some quantities based on our inputs with keys that correspond to our variables. And then we return our objectives and constraints in a similar dictionary. Once we define our problem, then what we want to do is incorporate our generator, which is our optimization algorithm. So Xopt provides a number of optimization algorithms for use kind of off the shelf without any modification. These include a number of different genetic algorithms, such as NSGA2 and CNSGA. We also have, I think a lot of our research and development has been into Bayesian optimization algorithms. And so these model-based optimization algorithms, there's a significant number of them incorporated for various optimization tasks that I'll talk about later in the talk. And then we have things like algorithms from control theory, such as extremum seeking, or heuristic-based optimization algorithms, such as RCDS and Nelder-Mead. And we're working towards incorporating additional optimization algorithms, such as those introduced by SciPy Minimize, things like reinforcement learning as we continue to develop our machine learning portfolio, and to start doing discrete optimization. And so once we combine these three objects together, we create our Xopt object, and then we're able to start, for example, explicitly evaluating points, visualizing the results, or running optimization. And I'll show an explicit example of this in the next slide. So this is a very simple example of running a Bayesian optimization. There's a tutorial linked here in the slides, which I'll share with the organizers. In this case, we're trying to minimize just a basic sine function. And essentially what we do is we start by defining our problem with our Vox variables and our evaluate function. We define our Xopt object, and then we run optimization by basically starting by randomly evaluating a couple of points And then in a for loop, we call the Xopt step method multiple times in order to run the optimization through multiple iterations. And what's important here and what makes Xopt more distinct than other optimization packages such as scipy.minimize is we have a much higher degree of control over how the optimization process is run. And so what this allows us to do is have the flexibility to visualize how the optimization algorithm is making decisions about performing optimization. So for example, in the context of Bayesian optimization, which uses a statistical model that we base on experimental measurements, we are able to actually view that model updating step by step and examine how it's making decisions in order to minimize our objective function. And so this flexibility is critical, actually, to using optimization algorithms in the context of both simulations and experimental contexts, where we really need a high degree of control in terms of when the optimization algorithm is running and being able to interrupt the optimization at any one point to view what's going on internally or to address, for example, issues with the accelerator or our simulation. And so this is an example of something more complicated. So this is us actually interacting with the physical accelerator control system. So in this case, what we're trying to do is a very simple problem. We're able to measure the transverse beam distribution on an intercepting diagnostic screen where the electrons hit the screen and they give off light that's captured by a camera. And what we're trying to do is minimize the beam size on the screen for one reason or another. In this case, our evaluation function has multiple steps inside of it. That includes setting the beamline parameters. So this is setting commands to the power supplies of magnets and the phase of RF radio frequency cavities. We wait for these power supplies to reach their set points. We then conduct the measurement. And then we do some post-processing to calculate our objective of interest. And this all happens within our objective function. And then when we want to run our optimization, we start by initializing our defaults with, for example, the current machine settings, and then we run the optimization using this for loop. And so what we get out of this Xopt object is essentially, well, for one, we're changing the parameters of the machine, but every time we make a measurement, we are dumping data to a pandas data frame that is contained within the Xopt object. And this data includes both the things that are pertinent to our optimization. So for example, things like the input values of our variables that we're adjusting, the output variables that we're trying to optimize, but it also returns anything that we put in our results dictionary. So in this example here, we return not only the total size of the beam, which is our objective, but all of the intermediate calculation steps. And in a lot of cases, we're able to return a lot more metadata that is critical to doing post-analysis of our optimization run. So things like the image file location on our machine in order to go back and observe what the images of our beam distribution are. Additionally, this data is, robust to things like NANs and interruptions to the actual accelerator, which is a much noisier and messier thing to interact with than just you would think that you would see in a conventional optimization problem, where we have, for example, interruptions to operations in the machine. And so we have measurement errors. And so this metadata that we include in the output will tell us why we didn't get a measurement. For example, the beam was too big on our screen, and so we weren't able to capture all of it, or there was an interruption in machine operations. And so this storing all of this data in a pandas data frame like this allows us to quickly and easily diagnose how optimization runs are going during the course of optimization. So now essentially what I'd like to do, now that I've kind of established the framework, what I'd like to do is go through a bunch of different examples that have, demonstrate how we are using Xopt kind of in the field in accelerator physics. So the first thing that I want to talk about isn't actually optimization itself, it's characterization. And so in this case, what we'd like to do is we have a large number of parameters that we would like to characterize our beam distribution across all of these parameters. But in the context of accelerators, there are certain accelerator parameters that affect the beam distribution a lot more than others. And additionally, we have very tightly constrained parameter spaces. So you could imagine that we're trying to propagate this beam down this tube. And for example, if you steer the beam one way or the other with a magnet, it could potentially hit the edges of the tube and then the beam would be destroyed. And so we have, a very tightly constrained space over which we can do this characterization. And it's a complicated space as well. It's not rectilinear, so we can't just specify variable bounds in order to do this exploration. And so usually how this is done by human operators is they will take each individual parameter and do a manual mesh scan, which of course does not scale very well to higher dimensions. If we consider, going to maybe 4 or 10 dimensions, the number of points that we need to measure scales exponentially with the number of dimensions. And so by using Bayesian optimization techniques inside of Xopt, we do a exploration-based optimization, if it were, which essentially learns the functional dependence of our objective on our input parameters and does more frequent sampling along the along the dimensions where the input parameters are determined to be that they have a larger effect on the thing that we're trying to characterize. And so this has substantially speeded up our ability to characterize beam parameters of interest. So in this example here, it took human operators 5 hours to scan 4 parameters. But using this exploration technique, we were able to characterize the dependence of our objective on 10 variables in 2 hours, which is a substantial amount of speed up. And we're using this data actually to train machine learning models to replicate our experimental measurements without having to do them in the first place. In terms of optimization, especially in higher dimensional phase spaces, we have this example from the European Synchrotron Radiation Facility in France, where they have 28 magnet parameters that they needed to optimize in order to maximize the amount of time that the beam exists in the storage ring. So basically, they send a beam into a circular accelerator, and over time, the beam particles get lost if the dynamics are not being controlled well. And so this corresponds to lifetime, essentially. And so this is controlled. They have a very large number of parameters. I think it's up to 130 parameters that they could potentially tune. But in this case, we tuned 28 knobs with a special type of Bayesian optimization known as trust region Bayesian optimization, which adaptively scales the search region, and it shrinks and expands the search region based on how successful we are. And so this allows us to scale Bayesian optimization to very high dimensions. And using Xopt in this experimental setting, we were able to get the highest lifetime that that facility had ever seen at that time back in 2024. We can also do online multi-objective optimization. So in this case, we have multiple competing objectives that we want to identify the ideal trade-off between these objectives, and the so-called Pareto front. And so usually this is done using genetic algorithms, which create genetic algorithms work very well when you can evaluate things in parallel. So you can evaluate a population of potential solutions in parallel. But in reality, in the real experiment, we only have a single accelerator. And so we need to do this sequentially. And so in order to do this, we have something called a multi-objective Bayesian optimization, where in this case, you create surrogate Gaussian process models of each objective that predict where in parameter space future points will maximize something called the hypervolume of the Pareto front, which is this volume of that's taken up in a Pareto objective space between your reference point and your set of non-dominated points. And so as a result, this can be used sequentially in a very efficient manner. And so this was an example of us applying this in an experimental setting is the SLAC MEV ultrafast electron diffraction beamline, which is used to characterize crystals and different material properties. And so in this case, we were able to quickly and efficiently find the optimal trade-off between the spot size of the electron beam on the sample and something called the Q resolution, which is essentially the resolution in Fourier space. And so this allows experimenters to identify the ideal trade-off between these two objectives and then to select the working point that they want to use for the actual accelerator in this case. The other thing that we can do that we've done most recently in Xopt is incorporated kind of hybrid models. So in this case, when we have an accelerator facility, the accelerator facility has been running at this point for tens of years. I believe SLAC just celebrated its 50th birthday a couple of years ago. And so what we're able to do is take this large corpus of historical data and create a neural network machine learning based surrogate model of our objective function. However, this surrogate model doesn't perfectly capture all of the features of our real machine because there are things like temperature shifts and seasonal changes in the performance of the machine. And so we incorporate that into a Gaussian process model that we use for Bayesian optimization inside of Xopt to greatly accelerate our optimization towards the optimal configuration without, while still being able to take into account the small differences in the real accelerator, between the real accelerator and our surrogate model, and adapt to those differences as we measure them. We're also using Xopt to orchestrate a wide array of numerical optimization problems in simulation. So an example of this is doing model calibration, where we have beam dynamic simulations. So these are based on physics principle calculations of our accelerator facility. So in this case, this is an accelerator called FACET-II. And so essentially what we're trying to do is adjust the parameters of our simulation such that our simulated predictions match our experimental measurements. And in this case, we have a collection of experimental data. This is maybe 150 to 300 measurements. And to do that full comparison, we actually need to simulate for every measurement. We have to run a simulation to do the comparison. And so in this case, Xopt is orchestrating the parallel evaluation of a large number of beam dynamic simulations in order to compare their predictions to experimental measurements. Then you adjust the parameters. So the parameters of the simulation are your optimization variables. And eventually, you hope that your optimization succeeds and you start getting reasonable comparisons in your simulation predictions that aim to match your experimental measurements. Much more recently, we've started, now that we've been able to achieve single application of Xopt to single optimization problems, we can now start chaining together multiple optimization runs to not just optimize parts of the machine, but actually do start-to-end configuration of entire accelerator beamlines. So this is an example of this at the FACET-II facility at SLAC. And in this case, the operators, when they start up the machine, they have to run through a series of optimization and configuration problems in order to transport the beam distribution with high quality to the users. And so in this case, what we do is we take all these different Xopt optimization algorithms. So some of these are machine learning based algorithms, others are heuristic algorithms, and then we also have those from control theory. And all of those are combined into a sequential execution where we essentially go one by one and set up the machine completely autonomously. And so this is an example of that. We do, for example, a laser alignment onto the photocathode that produces the electrons. We have to do phase scans to to optimize the timing between laser pulses and RF fields. Then we need to optimize, do tomography in order to optimize phase-based distributions of the beam. Then we need to steer it through the beam pipe itself, and then set up diagnostics to measure measure and optimize other properties of the beam distribution. And so normally this whole process takes operators on the order of an hour and a half to several hours. And we were able to take this, standardize the process, and bring the runtime down to approximately 21 minutes, while the operators were standing by to observe the process, or to just honestly do something else that is probably more interesting than doing these basic accelerator control tasks. We've also deployed this on the start-to-end workflow on a diagnostic line inside of one of our accelerator facilities. So in this diagnostic line, we're able to pick off portions of the beam distribution as it goes to the main accelerator facility and make tomographic measurements of the phase-space distribution. And so in this case, we have to solve, again, a series of sequential optimization and control problems, including beam steering and focusing of the beam distributions, as well as phase-based tomography. And once we gather this data, this whole process takes about 5 minutes. Once we gather this data in an online fashion, we're able to send it actually to a high-performance computing cluster. And that will actually solve the inverse problem of determining our phase-based distribution from our 2D projections when we did tomography. And then this process repeats every 5 minutes in order to do a time-dependent characterization of how the beam distribution evolves over the course of an operating shift at the accelerator. And so because this would normally take a dedicated human to do all this process, this beamline has never really been used for this purpose previously, because we never really had the manpower to have someone continuously station this diagnostic line. But now, because we have autonomous control of these accelerator elements, we are able to do this time-dependent characterization. So that is enabling a new capability inside of our accelerator facility. So let me come back and just look at back to our kind of ecosystem. So we covered Xopt and where we're using it inside of the context of doing high performance optimization on a computing cluster. We've talked about the development of new online control research and development of these different optimization algorithms. And now we can start talking about production-ready optimization using the Badger GUI interface. So this is just kind of a screenshot of the basic Badger interface. Essentially what it does is it allows users to define the same things that we've been talking about in terms of variables, objectives, and constraints for our optimization problem without having to directly interact with the code itself. So for example, in this middle panel here, you'll see that we're defining a bunch of optimization variables where we can adjust their min and max values either manually or automatically based on the current settings of the machine. Then we can specify things like initial points and edit those points explicitly. Then we specify our objectives. And then on the right here, we have a panel that observes the process of optimization. So these objective plots and variable value plots will show in real time what the objective function is per iteration and what all the variables are. And then on the leftmost panel, we save all of this. Every time we run one of these optimization runs, we dump all of this information to a data file that can be reloaded into this graphical user interface to run multiple times if necessary. And this is important because in the context of accelerators, we're often performing the same optimization tasks multiple times at, over the course of a month in order to reconfigure the accelerator as necessary. And the interface, provides kind of a play pause such that operators can start and stop the optimization without interrupting the overall control flow. So this is also made to be, we put a lot of effort into making this facility agnostic as well. So just like Xopt uses a generic Python function to evaluate, to set the variables of or set the parameters of the machine and evaluate the objectives and constraints. We have a standardized interface that we define called the Badger environment. And so this is a Python class that requires the users to implement a number of required functions. So getting the current status of certain variables, setting those variables, and then getting observables, which can be used as objectives or constraints in our optimization. And then there's an additional set of optional parameters that allow you to, for example, search through the thousands of potential variables that could exist on a system, getting the bounds of those variables, mainly convenience functions. And so in addition to kind of the basic features of visualizing the optimization performance, we also have specialized diagnostic utilities that allow users to visualize in real time how the optimization is progressing. So one example is just visualizing the process of Bayesian optimization. So in this case, just like the previous example that I showed a few slides ago, we're able to visualize how the model evolves over time as we gather data, and then shows the acquisition function, which is how the optimizer is making its decisions. For multi-objective optimization, we do online Pareto front visualization and hypervolume computation so that users can determine when the hypervolume has converged. And so that's a moniker that they found their correct Pareto front. And so as a result, because of all of this development into the graphical user interface, operators are routinely using Badger to solve optimization problems at SLAC with a variety of different optimization algorithms provided in Xopt. So here are some examples. So one is the free electron laser pulse intensity at LCLS and LCLS-II. Then there's phase-space emittance, which is a metric of the quality of the beam distribution. And then finally, in this slide, I'm showing energy transfer optimization inside of the context of something known as a plasma wake field acceleration, which uses a plasma to accelerate a beam using another electron beam. And so in this case, they're maximizing the energy transfer ratio between the two beams. Additionally, Badger and Xopt have been used at a wide number of other facilities for various applications. So for example, this is examples of the use of Badger at places like the European Synchrotron Radiation Facility in France, the EU XFEL facility in Germany, multi-objective optimization at Fermilab, beam focusing at Brookhaven National Lab, and then a low energy beam transport at the ISIS neutron and muon facility there in the UK. More recently, with the popularity of agentic AI and large language models, we started incorporating that into the Badger workflow. So one thing that we've noticed is that it's difficult potentially for users to set up routine optimization problems inside the context of Badger. And one thing that we can do is use something called the Osprey framework, which is a community-developed agentic AI harness for things like Claude Code that has been developed across the Department of Energy facilities here in the United States. This agent was able to go through and look at previous optimization runs and synthesize a new optimization run in a text file format and then it proposes that run to the user, and then the user accepts whether or not they should run it, and then the agent will go through and run the Badger graphical user interface in front of the user, and that led to significant FEL performance. So this is the first demonstration of agentic AI-based optimization and control at an accelerator facility at SLAC. One thing that I've kind of noted throughout the talk, but really want to highlight here, is that Xopt and Badger, this framework, has been built as a community resource by the accelerator physics, or by the machine learning for accelerator physics community. So we've done a lot of research and development at SLAC, but of course there has been R&D into online accelerator control using machine learning and advanced optimization algorithms at a wide number of other facilities. And we are all kind of contributing to this single community-based optimization framework such that it can be used at, such that the same algorithms and the same research developments can be used at a wide array of facilities. And so as a result, Xopt and Badger, like I stated before, has been used at accelerator facilities across the United States and worldwide as well. So with that, I'd like to conclude and say that, the Xopt ecosystem is a flexible, extendable framework for doing advanced optimization, where we're leveraging our machine learning research and development into improving accelerator control. And while this talk has all been about accelerator physics and the development, the research and development that has gone into Xopt has been motivated and focused on solving problems in the context of accelerator physics, all of these algorithms are agnostic to the problem that they are being applied to. And so these could be very easily used across scientific domains. And we welcome any collaboration, from outside of the accelerator physics field. I want to also thank all the people who, contributed to these projects outside and inside of SLAC, and I'd be happy to take any questions.
Great. Well, thanks, Brian, for that really fascinating talk. If anybody's got any questions, please feel free to either raise your hand or can drop a question in the Q&A. I'll read it out. Just give people a second or two to do that. I'll ask a quick one now. So you've sort of preempted my question here with your last point in the end here with the fact that you can use this for many different science domains.
Yeah.
Have you had any conversations with industry? Like, so I can imagine this being useful in control systems in industry, say in manufacture or in petrochemical or any number of areas. This could be interesting.
Absolutely, yeah. So there is private industry in the accelerator physics space, especially recently with the development of free electron lasers for using it for semiconductor chips and EUV lithography and that kind of thing. So there is some there. There has also been kind of limited acceptance in other fields, things like, let's see, timing systems for stock trading, that kind of thing. And so the acceptance is just based on the popularity and people, stumbling upon or, collaborating with us on, that's the level of facility adoption that we've seen so far. But of course, I think it would be more relevant outside of the industry that we're interacting with right now.
Mm-hmm. Yeah, it could be a nice way of bringing money into SLAC if you could find like a licensing
Absolutely. Yeah.
mechanism for industry.
Yep.
Okay, I see we've got a question from Matthew. Let me see if I can just see if I've allowed your mic. You should be able to ask your question now.
Yeah, thank you. So my question's regarding slide 18, so the sequential inference. I guess firstly, do you know what algorithm you're using to sample the posterior in this case for the next prior?
Yeah, so in this case, so what we're using is an acquisition function called expected hypervolume improvement, which is actually implemented by BowTorch, which is developed by Meta and Facebook. In this case, we are drawing samples from each of the Gaussian process models, and I believe it's using. I'm sorry, it's it's using the reparameterization trick in this case to draw those samples. So essentially, you draw Gaussian distribution samples and then transform them based on the form of the Gaussian process model.
Okay,
and then
sorry.
Yeah. And then you use those samples to estimate the value of the acquisition function, and then you maximize the acquisition function. Sorry, go ahead.
I was going to say, so you don't directly use the posterior from one analysis and go to the next?
We can, if the posterior is analytic, and we can analytically compute the expected hypervolume improvement. But if we want to keep this as general as possible, the sampling approach is better. Just to allow for the use of things like observable constraints and non-Gaussian likelihoods, that kind of thing.
Okay, thank you.
Yep.
Yeah, I think that answers my second question anyway. Thank you.
Yeah.
Great. So we've still got some time for some more questions. If anybody wants to kind of raise their hand, until I've got another one. So on the slide where you were talking about chaining these different instances of Xopt into like an autonomous setup. So do you have any so presumably because like one is kind of feeding the next one, do you have to sort of consider any different treatment of propagation of errors that you might sort of expect to see if you were just doing this as like an individual person, kind of like step by step? And then sort of as a secondary question to that, do you, for this problem but also these problems in general, do you need to have like a human in the loop at any point, or is that like a sort of, I don't know, like a Luddite holdover that we sort of feel like we need to have people involved, but maybe we don't?
Yeah, so in between, so what's not shown here, because I'm highlighting the optimization aspects, is the huge amount of software infrastructure that's necessary to, for example, recover from errors. and make decisions about which optimization algorithm to run at what time. So in this case, basically, we are doing something that is fairly naive, which is just running through it in a sequential manner. And the optimization algorithms don't really interact with one another besides saying, I'm done, you're the next one to go. And so that is obviously not ideal. What we'd like to do is, and I think this is where a lot of potential agentic AI-based orchestration can come into play, is that the optimization, each of these individual optimization algorithms talk to one another in kind of the similar way that we would communicate, where they would say, oh, I ran into this problem, which each algorithm says, I ran into this error, and the agentic AI decides, well, should you retry? Should you try and run more iterations? Should you retry the optimization from scratch? Should you try a different optimization? And so that kind of enhanced decision making is what we're looking to enable next, where these basic optimization steps are like the building blocks or the tools that the agentic AI would utilize to do the start to end operations. And so in this case, in this demonstration, there was no human interaction. It basically just ran by itself through the 21 minutes. And so that requires a very basic kind of control flow in between these optimization algorithms and enough exception handling such that you can kind of hard code exactly what you should do if you get an error or something. But eventually, and as a result, if you incorporate an error that you can't handle or that you're not planning on handling, then it stops and kicks back to the human. Hopefully, the agentic framework will handle the edge cases that come up. Then we take the human kind of fully out of the loop.
Yeah, and I guess the more operation that you have, the more of these edge cases that you see.
Sure. Yeah, absolutely.
Okay, we've got a question from Daniel Marks. I'll just read out the full question. I'm sure there must be similar tools developed by people in other scientific fields and industry. Since you mentioned Xopt is domain agnostic, what's unique about it, and why was there a need to develop your own tool? Does it particularly interact well with Accelerator data?
Yeah, so I think when we started Xopt and the Xopt development, we had two problems that we had to solve, or two issues that we ran into that kind of motivated the overall development. The first is we had a bunch of different optimization packages out there that implemented all these great optimization routines. But the interaction with those packages was not standardized. And so it's very difficult if you wanted to go try out different optimization algorithms. You would need to spend a lot of time building the connective tissue between those optimization packages and the problem that you were trying to solve. And so Xopt was aiming to unify both the broad scope of optimization algorithms that we use inside the context of accelerator physics. So for example, Bayesian optimization, one of the well-known packages for this is AX, which is based on BowTorch. And then, for example, genetic algorithms, you have things like PyMu, and there's other things out there. Then there's the SciPy minimize interface. And so all these different interfaces are different. And so it makes it difficult to connect those to simulation or experimental problems. So that's the first problem that we ran into that we tried to solve, is that Xopt does not implement a single type of optimization algorithm. It incorporates all of these different ones under the same framework. The second problem that we have is the flexibility of being able to interrupt and dive deep into what's going on internally inside of the optimization process. So for example, if you use SciPy minimize to optimize a problem, just basically, it will go through and you have callbacks, but that's kind of limited in what you can do. You can't like interrupt, delete some data from it and then restart the algorithm. And that's where this decision was made to not fully put the optimization loop within just a single function. We put it in this object-oriented way that allows users to interrupt and make very complicated workflows by modularizing and breaking up the fundamental optimization loop that is within this x.step function. And so those were the real two needs that we aim to satisfy with Xopt, which are relevant to scientific facility operations, essentially.
Okay, cool. I hope that answered your question, Daniel. I think we can wrap it up there, unless there's any like last hands go up. 2, 1. Nope. Okay, well, thanks again, Ryan, for a really great talk. And we can finish up there. Yeah, thanks very much.
Yeah, I'll just mention that if anybody is interested in working with us, please send me an email. We're happy to collaborate and do development as people need it.
Great stuff. Thanks, Ryan.
Yep, thank you very much.